today's lecture, composites, material selection. I'll do the composite stuff, Graydon will do material selection, and then cover some resources that we have available to us to aid in our material selection. Starting basic, what are composites? So it's a combination of various materials. They come together with some unique physical and chemical properties that neither material or component of the composite material has itself. Some examples of that are carbon fibers, flax fibers, or fiberglass. Now, if you look at these pictures, we have the M4 GT3 car, which is a full carbon body. We have our exhaust here, which has a carbon muffler, and then some wings there on the fabric itself. So when we make composite materials, we generally, like I said, have this fabric, and then with it is a matrix of sorts, so generally a resin, which gives it that stiffness, but doesn't really add too much strength. There's a ton of applications of composites, specifically aerospace, so planes, rockets, that type of thing. Construction, sports equipment, so like rackets, bats, and then obviously the automotive and motorsport industry. A little game, just like off of intuition, try to guess which one you think would be made out of a composite material and which one wouldn't. This is like a rear wing flap on a McLaren Speedtail. Composite or not a composite? Okay, it is. Yes. Good, yeah, you're one up. Okay, next one. Locked in. Okay, you're right again, so I guess you win. Third one here, A-pillar of a car. That is just metal, yeah. So if you if we look at the first one, we see more of organic shapes in the body lines of the car. Composite materials tend to be a little more organic in terms of their shapes, just because hard edges and stuff have really high stress points. Now, like the bumper, for example, if we go back to the M4, it is all carbon and the bumper is fully carbon. But for production cars, that's super expensive just because of the time it takes to manufacture it. So something like the bumper would be like an injection molded plastic. And then the A-pillar is aluminum in this case. Because again, it's not a very organic shape. You see all the cutouts and stuff. It doesn't work really well with composite materials. So we'll go through the advantages of it. The weight to strength ratio is really high for composite parts generally. When you manufacture them right, they can be a lot lighter than traditional materials, while being the same level of strength or even stronger. Many and most of them are corrosion resistant. If you look in that top picture there, we have a wind turbine blade. Those are fiberglass, and those are corrosion resistant. There's a ton of design flexibility. So with composites, since it's a really broad range of materials, you can have like fabrics like we use in the car. You can do particle stuff or like forged carbon, which allows you to get a lot more complex shapes. And then you can really like tailor the properties of the composite material itself. So depending on the different, like the matrix you use and the reinforcement, you can alter the characteristics of it to like directly apply it to whatever application you need it for. So it can be like different strengths, if you're looking for strength, weight, or thermal resistance too. You can change your combination of reinforcement and then the matrix as well to make sure that those are optimized. Go through some different types. So the most common one I think that everyone would know of would be fiber reinforced composites. So that is like your carbon fiber or your fiberglass. That's where it's generally a fabric. Like that top picture is fiberglass, that's a fabric. So just a woven material, and then you will either infuse or like lay up, just through a wet layup, an epoxy resin into it to give it that strength. We have particulate reinforced composites, which use like a powder or small particles. So yeah, in this one, like silicon carbide particles, that's an example of a composite that is made with particulate reinforcements. And then laminates too. Laminates are it's more of a fiber reinforced composite because it's just the like layering of different fibers and plies on top of one another. Okay, some types of reinforcements here. We have glass fiber, which is fiberglass, carbon fiber, which our car Mark IV has a lot of. Kevlar, which is like military helmets or bulletproof vests, those are Kevlar. And then some organic ones such as flax, hemp, and bamboo. So that seat is made out of flax fiber, and that body panel on the car there is hemp, and then that bottom one is carbon fiber, obviously. So there's a ton of different uses for each one. The organic ones are still like pretty new in terms of the composite materials. So a lot of very structural stuff isn't made out of them yet. It's made of more traditional composite materials such as fiberglass and carbon fiber, but definitely something interesting going forward. And then when we talk about reinforcements and the orientation of them, these different geometries vary a lot. So when we look at the pictures there, we have unidirectional. So that is where the fibers themselves are just in one direction. They're not woven at all, so there's no weft or waft in between those fibers. It'll be really strong in tension, not very strong in out-of-plane loading. So like if you applied a load this way across the unidirectional composite material, wouldn't be very strong. Anything in tension, so like pulling them apart, super strong. When we look at the laminate, that's where we like lay many layers on top of each other. You can see in that very first layer where we have the 090 fibers, that would be a woven material. And then the one that goes across on a 45-degree angle would be the next layer of the laminate. So you do all of those directions and you'd cover kind of every single direction that that part would be exposed to in terms of force. Chop fiber would be your forged carbon fiber components. So that, in terms of manufacturing, allows us to get a lot more complex shapes, but it also provides strength in every direction. So in this picture, the fibers aren't touching and overlapping. In practice, and when you manufacture it, all those fibers will be connected together through the resin matrix. So it'd be able to provide strength in every direction. Again, kind of like that laminate, except like it doesn't matter where the force is applied. There's still some instances in the laminate, if you applied it, I guess, from the side, where you could separate the two like plies, but in a chopped composite, you wouldn't have that same failure. And then particles is the same thing. Particles, there's a lot more failure modes you have to be aware of, which I'll go into here. So this in general, like any material, composites will fail. There's pretty specific ways that they fail depending on what type of composite material you have. If we look at the top, we have fibers again, so that's your woven stuff. In tension, which it doesn't tend to fail in because that's where the strength is. You could have stuff like matrix cracking, so that would be the resin itself and not the fibers. The resin would break. The next one over is fiber fracture, which is pretty rare because those fibers are so strong. If you take a like T300 carbon, which is just a strength rating, it has a strength and tension of about 3,500 megapascals. Like the fibers themselves won't snap until that much pressure or more is applied to them in tension. So that's pretty rare. And then compression is a pretty common mode of failure just because the composites themselves aren't meant to be put in compression. They're really strong in tension, not in compression.
And they're supposed to break anyway. Like for aero, I think like the front wing should break.
Yeah, so it'll have some flex in some directions, and a lot of composite parts are made like that. So that in one direction they'll be really strong, in the other direction they might have a little bit of give. And then on the bottom we have particle composites. So the plastic constraint is when the resin itself will plastically deform between the particles, not separating from the particles, but just the resin itself will. Decohesion is where in tension the resin matrix will pull apart from the particle, as you can see there. So on the top and the bottom there'll be voids. And then decohesion is in compression, and again it'll separate similar to the first decohesion, except in compression it'll kind of squeeze out along the sides of the particles. Another thing is heat. Composites can be pretty susceptible to thermal failure, depending on what it is. The fibers themselves generally aren't, but the resin matrix is. For example, our exhaust, it got really hot, so you can see where the resin started to melt, and it's just fiber now. There's no more resin left. So that's another really common mode of failure. And then for ourselves, where do we use them? Nearly all of the in-house made body panels and stuff on Mark IV are composites, same with Mark III. Mark IV is all carbon fiber, where Mark III was a lot of fiberglass. These pictures here, that first one on the bottom left is the nose cone. That middle picture is some wing elements. So that was last year for the rear wing. That's the main element and then the second upper element. That's after a wet layup and then inside of a vacuum bag. So after we've laid the fabric onto the airfoil, put the resin into it and then put it in the vacuum bag in order to provide compression when we're curing it. And that third one, that larger picture, is the hood. So that's the outer layer of the hood inside of the tooling. That's before any resin is put onto it. So that's just the fabric itself.
So for material selection, totally different topic, but sort of same-ish. It's really important to think of the purpose for what your material is going to go through, whether what you're designing is meant for your braking system or it's meant for your chassis. Perhaps it's meant to hold liquids or otherwise. It needs to have certain properties which will allow it to behave a specific way. Take example on the screen, airplane wing. Needs to be strong, needs to be stiff, needs to be tough, needs to be light. If it's not stiff, it'll be flexible and you'll flap like a bird. If it's not strong, it'll yield. If it's not tough, it'll break. If it's too heavy, it's not going to fly. Which, for a lot of, at least for vehicles in our case, performance comes down to not tough enough, not strong enough, not stiff enough, not heavy enough, or not, sorry, too heavy. Obviously, we want to try and optimize those. For other kind of shapes or other kind of things you might be designing later on in other jobs that you go to, perhaps you want something that's really heavy for some reason, whether it's weighting a base for some kind of machine, or if it's something that's not tough at all, so that it'll break off, like the bottle cap and that little tiny rim that kind of holds it sealed. So lots and lots of properties. So we got general ones like density and price, lots of mechanical ones, thermal properties, electrical properties. Can you guys name any properties that aren't on this list? Thickness, so thickness is important. It's not a property, it's a material feature or geometry, right? No, so the difference between intensive properties and extensive properties is whether it's involving mass or not. So something that would be an intensive property is something that doesn't include mass. It's independent of mass. Yeah, so something like density is an extensive property because it has kilograms or mass involved, but something like thermal diffusivity doesn't, right? It just has to transfer through some medium, a distance, but it doesn't require any kind of mass involved. But it's not a material property. To say that this piece of wood and this table leg are the same because they're the same length, any material could have those lengths. Having a piece of aluminum that is at 100 degrees Celsius doesn't make it the same as a piece of plastic at 100 degrees Celsius. It's like a little different. They could have the same hardness. So when you're thinking about, okay, I want to get like property selection down, I got some ideas, I'm not sure where to start. How should I frame my question so that I can actually start working on developing a procedure to find what material I'm looking for? It's important to think about the material, of course, but also the function your material is going to be used in, the processes that your material will have to go through, and then the final shape that you want to get. So remember how Kai mentioned in the Composites lecture that aluminum A-arm for the car was made of sheet metal. It had lots of holes in it, lots of complex geometry. You would use metal for that because the final shape has lots of holes punched through it, and you could try to do something like that with composites. But the process to do so would be super difficult. You could get the final shape, but the process is really, really... So looking at your constraints is really important. Simple constraints. My material must be magnetic to be worthy for what I'm doing. It must be very hard. Objectives for what you want to complete to make it stand out. So a lot of materials will have what you want to achieve. Will be able to achieve what you want to achieve. But in order to make sure that you choose the right one, you need to have something that defines what is the excellence. What are processes? We talked about material, we need to talk about function, we kind of did. Processes and shape. Processes are methods of making and methods of combining materials. So joining, such as adhesives, there's a thing called the impact attenuator. It's a big block of aluminum that we use adhesives to stick to the front of the car. In the event of a crash, the impact attenuator will compress and in such will absorb energy away from the driver. That is held on with adhesives. Welding. Steels you can weld, aluminum technically you can weld, but welding's super common in our shop. Fasteners, we had a whole lecture on that. Can you guys think of any other methods of joining? Yeah, friction stuck or what's it called? Interference fit? Yeah. Shaping. Shaping's a really big one. That's what most of the machine shop is for. Machine shop would be considered processes of deformation. The picture I have here is turned on its like upwards, but it's a lathe, and it's a deformation process because it's removing material and it's deforming the original shape. As your cutting edge comes across, it's removing material. Similar to a lathe, you can use mills, band saws, grinders. Casting, you have a metal, you make it liquid, you put it in the thing, you let it harden, and you get the shape out of it. Molding, similar. I think you mentioned it earlier, injection molding. It's where you can fire hot plastic into a similar kind of mold. It cools really quickly and you pop it out and you get your plastic shape. There's also negative molding, so not negative, it's not called negative molding, but it's the mold of a negative where you take something, you stick it in some kind of medium, that medium assumes its shape. Think of dentistry, if you ever had braces and you have to put that gum stuff in your teeth. That's an example of getting a shape of something, which you can then use, you could fill it up with a mold. Powder is a neat one. Imagine you had a box full of sand. And you said, I want to make this sand into a block. What could you do? You could step on it a bunch, compact it down, and eventually if you step on it hard enough and long enough, you're going to get a brick. That's kind of what powder is. You can compress things into a shape. A final shape is other ones like laser sintering, which use a thin layer of powder, which you take a laser over and you burn it, or like sinter it, into a layer. And you add another layer of sand and you sinter that and you add it. So it's a type of, you can think of it 3D printing or another additive manufacturing where you're just adding layers of sand and eventually you get this complex shape. Laser sintering is really powerful because it also allows you to make complex molds out of it, because if it's made out of sand or some kind of other medium like that, it might be mold casting compatible. Finishing. You have your part, you just finish crafting it through the mill. Now you want to give it a nice polish, make it look shiny. You want to give it some paint, make it look purple, give it a coating. This doesn't really apply to us, but it's worth considering. Material has personality. And you should think about your material and you should be kind to your material because it has feelings. Now, when you think of material, think of these three things: aesthetics, associations, perceptions. Aesthetics being your five senses. Associations, what does it remind you of? Perceptions, how does it make you feel? So, listing some attributes, it has both the positive and negative, or you can think of the one side and the other side of how it looks. So you can think of it being humorous or serious, classic or trendy, cheap, expensive, right? It's important to think about, what about the aesthetics of those materials? Is it hard, soft, cold, or warm to the touch? All of these, when you make your final product, you should take into consideration. When you're making something for someone else, wherever it might be, consider what your end product will actually do for the end user. I mentioned it earlier, but shapes are huge. For different use cases, different shapes will have different reactions. A good example is a hollow cylinder. Think of a toilet paper roll. I didn't bring one today, but you can still think about it. If I stand it up so the roll is facing upwards and I'm pushing down on it, that toilet paper roll can take quite a beating. It can take quite a lot. You can probably almost stand on it if you wanted to. If you put it on its side and you push down the pinky, it'll fold on itself. For chassis, which is what I did a lot of, I was dealing with round tubes and square tubes. Round tubes, great for compressive and tension along their axes. Square tubes can also handle it, but what they can handle better is compressive forces on their faces as well, which makes them great for things that have, or things that you're mounted to them, like the front bulkhead where the attenuator is. Those forces are translated onto the faces of those tubes. When those tubes are square tubes, they can handle more. And in fact, the SES, which is how we submit our tubing requirements to FSAE, you can choose between round or square tubing for that portion of the chassis. If you do choose square tubing, it puts out about a bunch of math, and using these equations, it decides that the minimum thickness for the tube required, the minimum thickness for square tubing versus circular tubing, square tubing could be thinner in that case because of what it's used for in front of the chassis. Some other stuff that I'm not going to mention tonight because it's just kind of beyond everybody. I wanted to throw it up here, but material indices, this right here on the side, are material indices for different types of situations. Material indice is a combination of relevant material properties which will indicate which one you should choose and how you should gauge other materials. And so those weightings influence how you should choose them. I'll show you in a second how that works. Penalty functions, whether or not you can think of it kind of like a weighted matrix. Material trade-offs are what these figures are, where you have trade-off lines where certain materials fall under certain parameters, I guess, will be better. In this corner, I have really expensive and lightweight, carbon fiber perhaps. I have super cheap and heavy, steel. And I have really expensive and really heavy. If there was a super lightweight, super cheap thing, it'd be used everywhere. So getting onto some resources. Knovel, I'm not sure how else to say it, is a nice website for students. It looks like this. On it, you can convert units. So if you ever try to find, like, oh my goodness, I couldn't find molar enthalpy or specific enthalpy. Through this, you can look up a ton of different material properties. If I expand a bunch of these, you can see the kinds that are here. If you needed to find a very specific material, you could use it by searching this. What if you wanted to have a more general look? There's ANSYS, Granta, EduPac, a whole suite. This is ANSYS Granta, which is a material database. I'm on the level 1 database. There's a lot of different databases. Level 1 is the most basic and most general. If I look up all materials, it gives me a list of them. I can look up metals and alloys, non-ferrous, aluminum alloys, and by clicking it, it gives me descriptions on basic aluminum alloys. This is for level 1. If I decide to change it, if I go home, I change the database to something like level 3. You can see it instantly gives me a lot more. And when I go into metal and alloys, it asks me a lot more. If I say I want non-ferrous aluminum, I want cast aluminum. Actually, no, I want wrought aluminum, 6000 series. I want 6061. I want T4. It'll give me more specific data on that material. This is how David actually decided what material he wanted to use for his cast uprights. Super, super handy. Say you don't know exactly what material you want to search off the bat, we can go ahead and do that. That's where material selection comes in, right? You get the idea. Level 3 is much more difficult. It's got a lot more things it's got to consider this time around. Like a lot more things it's got to consider. Thank you for attending. What?
Door was locked.
No. Oh my god.
Like half an hour. A lot of people try to get in and they like.
How many is a lot of people?
Only a couple.
Oh, okay. Well, that's,
2 or 4. But anybody who tried to come in, as soon as 8 o'clock hits, it locks.
Was it?
You don't hear us banging on the door?
no.
No, it's double door.
Freak. I'm gonna stop the recording now. Bye.